Hello and welcome to my video on dynamics, which are forces, and this is the introduction video to this. So let's just dive right in. So to start with, there are different types of forces, and so there are going to be, we're just going to list them here, and there's some nice piece of information for each of them. So the force of gravity, which we label, and the labels are helpful to know about as well. Force of gravity is Fg. Which is always mass times acceleration of gravity, which is g. And so g, just by the way, is equal to 9.81 meters per second squared. Okay, and the normal force is often also mg, but not always. The normal force is actually, more specifically, equal to the magnitude of the component of gravity going down or opposing the surface. So the normal force is always perpendicular to the surface, and the component of gravity that is also perpendicular to the surface, it will be equal to that. Now that becomes more important once we look at angles and a inclined plane, which happens in our next unit, 2D vectors. So in this case, that's why that changes. Or let's say you're underwater, and I guess I could add another force here, which would be the, you could say the buoyant force if you're underwater. So I don't know, we can call it whatever we want, but probably like FB. So the buoyant force would be certainly another option here. So if buoyant force is pulling up, then the force of gravity seems less, the apparent weight is less, and so it's labeled as the apparent weight. So Fn, this is an important one, it's perpendicular to the surface. So the really big key thing here is that it's perpendicular to the surface. All right, and often mg, but not always. Okay, applied force is a force that's been applied by either a person or some sort of motor or something like that, by some sort of machine or person, and so we just say force applied like that. Force of tension, what's important about the force of tension is that there's always, it's always equal along the entire distance of whatever rope, string, chain, whatever that you've got. Okay, and we label that Ft. So this is important because if you have a pulley, let's say this is my pulley here going up to the ceiling, and we've got a rope coming up and across, and you're pulling here, you've got a little person and they're pulling on the rope. The force that this mass is being lifted up by is the same as the pull by the person, which is intuitively correct, but also definitely always correct, always equal along the entire string, rope, whatever. Okay, so until it's broken up by another mass or another pull or another whatever. Okay, so if there are multiple pulleys now, or multiple, not pulleys, but multiple masses, so let's say we've got a situation like this, where there's a mass down here pulling, mass here and a mass here. Well, this force of tension is equal to this force of tension, but those are not equal to this force of tension and this force of tension. So the red ones are equal and the green ones are equal, but they're not equal to each other because it's been broken up by the purple mass here, and that causes that to be two separate lengths of string. Okay, frictional force. Friction always opposes motion. This is really important. So whatever way you're moving, not necessarily whichever way you're applying a force, but whichever way you're moving, that or the opposite of that would be the frictional force direction. And here is the formula for frictional force. It's mu times Fn, and sometimes we can say, hey, Fn is mg because of before, right? But not always. It's not always, okay? Not always. It depends on if there's angles involved or whatever else. But it is always, frictional force is always mu force, normal force, mu times normal force. Okay, the next one is air resistance or force of drag. It'll just tell you this in the question, so you'll just have some sort of value. Okay, and the next one is the spring force. We'll look at this more later in the energy unit. So this is interesting, but not really, like right now it is a force, but we don't really have to deal with it quite yet. Okay, and we'll look at it also more in the unit when we talk about like pendulums and stuff, waves. So simple harmonic motion, that sort of stuff. So we'll talk about that a little bit more later. And buoyant force in water, pulling up. Okay, so those are all the different types of forces. Here are the steps to solving a dynamics question. This is really, really important. So feel free to copy this down somewhere, as this is the same steps I will take on the next couple questions on this video as well as the next video as well. So really important topic here. So draw a free body diagram. You should not include an F-net arrow in the free body diagram, just the real actual forces. Then you can start to go into F-net equals MA, as well as F-net equals force 1 plus force 2 plus force 3, all of the forces added. And you might have to do a separate horizontal and vertical F-net. So that will come into effect, again, this is more later in 2D vectors. But this is a very important thing that you have to be able to do by the end of the course, but it is in our 2D vector unit. Then rearrange and solve for the unknown, which I always say get the unknown on top and by itself using opposite operators and opposite bed mass. So this is important. So bed mass is just order of operations, meaning that we start with subtraction and we end with brackets. Okay, substitute in the known values and solve in your calculator using proper sig digs. So that is exactly the steps that I'm going to take right now. So let's go ahead and try this question out and see if we can answer this here. Let's just go like, I just want to go down a tiny bit. Wonderful. Okay, so our first step is to draw the free body diagram. Mr. Drager, maybe I'll just draw the situation. Okay, if I were you, I would suggest pausing the video right now, trying this question for yourself, and seeing if you get the same answer as me once I'm done. So pause it, and then try it yourself, and then press play. So Mr. Drager throws a ball up into the air. Okay, so this is the kind of picture, I guess. If the ball is that many grams, what is the net force on the ball while in the air? Okay, this is a very, very simple example. We're going to start simple and get more complicated, more so in the next video. But if we just think about the net force on the ball, well, what we need to do is we need to start with a free body diagram. So usually what I do with the free body diagram is I just draw a square or rectangle for the mass. And what we can do is simply label the mass inside. What I will say is maybe change that mass to kilograms instead of grams, since everything we do is in kilograms, in meters, and in seconds. It has to be these 3 units. So please always, always, always change to those 3 units. Okay, so anyways, we've got this rectangle. What are all the forces on this rectangle? So this is called a free body diagram. Now, there's only one force. It is the force of gravity. Okay, and we know that the force of gravity is mg, based off of our formulas. So now what we do, that's our first step. So I'm going to say that's our blue. Okay, now our second step, I'm going to do this in red, and maybe I'm going to change to a thinner pen. Okay, so now our second step is to do your F-net. So F-net equals MA. and equals all your forces added. Well, all your forces added, there's only one force, Fg. Okay? So now what we can say is, well, what are we looking for? Well, we're looking for, so I guess we'll do this in purple. Okay, we're looking for, what's our unknown, right? Our unknown is the net force. Okay, so we're looking for F net. So in this case, we don't even need the MA part. Normally we do, but in this case we don't. So F net equals Fg. And we could also say, well, F net equals mg. Okay, because Fg is mg. Okay, and then substitute in the known values. So this is F net equals, and then m is 0.123 kilograms. Gravity is 9.81 meters per second squared. And now we need to get our final answer. So now we're just going to plug this into our calculator. I just want to show this to you guys. That's part of the benefit of using this computer here. I can show you how I would be writing this into my calculator. So 1.2066. So 1.2066. And so I guess I did that, and now I'm getting my final answer. Whoops. So 1.2066, and this is force, which is newtons. And so now what we need to do is get our sig digs, and this is 3 sig digs because there's 3 values here. Well, actually we can see it, 3 here and 3 here, and so we get 1.21 newtons as our final answer. All right. Hopefully that made a lot of sense to you guys. It's a very simple example, but we have to start somewhere. Let's try the next version of this, the next example. So I'm going to do the same type of thing where we've got blue, then red, then purple, then green, then orange. So let's start with our blue. Our blue is telling us, well, we need to draw a free body diagram. So let's do that. Mr. Drager wanted to lose some weight fast, so he decided the best way to do this was to go on an elevator ride. He went from weighing 70.3 kilograms to 63.6 kilograms. I don't even know if this is actually this is accurate. I only know my weight in pounds, which is kind of weird. For a short time while riding the elevator, what period of time in the elevator was he this lowest weight? Okay, this is starting to become a little bit more of a complicated question. This is why we need to draw a free body diagram. The last one, you're thinking to yourself, why am I even drawing this? But this one, we need to think about it and we can figure it out. So let's think about the 2 situations in the elevator. So one, the elevator is moving up. Okay, so there's a platform and I'm there and it's moving up. The other situation, I'm in the elevator and it's moving down. Okay, if it's moving down, not moving down, accelerating up or accelerating down. Okay, if it is accelerating up, then we can talk about that as our F net value. Okay, so yeah, let's see if I can actually figure out. I also made these questions and I didn't actually try them out. So hopefully they actually work. So in this first part, if I'm accelerating up, that means the normal force is actually greater than the force of gravity. And we said that normal force is our apparent weight. So that's actually no good. I'm just going to make force of gravity smaller. Okay, so this one is no good because the normal force has now gotten bigger. Whereas in this case, the force of gravity is whatever the size is, and the normal force is smaller. You guys see that? Because it's accelerating down, that means the arrows have to add to go down. So Fg has to be bigger than Fn. Okay, so if that's the case, now what we can do, I guess I should have a little bit more detail from weighing when stationary. There you go. That's probably a little bit better. Yeah, I can't move that. Okay, that's annoying. Yeah, it's fine. Okay, so we're definitely going to use the bottom situation. So that's the situation that's going on. So now let's write our Fnet statement. Fnet equals MA equals Fg minus Fn. Okay, so normally, in the normal situation, Fg is Fn. Okay, so when stationary, this is the mass when stationary. So this is mg. Okay. I'm going to say m1. This is not quite accurate because I didn't actually weigh this much. I guess I should have had this in newtons. Yeah, not ideal. This should say in newtons because I'm weighing, but that's fine. On the scale, it will say that many kilograms. So, anyways, this is correct. And then what we're going to do is we're going to try to what was the elevator's force during this time? Let's say, actually, what was the elevator's acceleration during this time? That's a better question. Because now we can rearrange to solve for A. I guess you could just solve for the entire thing and call it a day, but this is a better question. So if we're solving for A, then we're going to divide by m1 on both sides. Okay, and so now what we can do is, yeah, I mean that's probably fine right there. So now we're going to plug this into our calculator. So 70, or actually, let's write it down first. 70.3 kilograms times by 9.81 meters per second squared minus 63.6 kilograms times by 9.81 meters per second squared over our normal mass, so 70.3 kilograms. Okay, now let's try this in our calculator. So we've got bracket 70.3 bracket 9.81 bracket minus 63.6 bracket 9.81 bracket 70.3, enter. So the acceleration of the elevator was not much, but will be, or would be, 0.934. So let's just say this. We'll use purple. 0.934. What else? 95. Okay, and this is meters per second squared. Okay, because it's an acceleration. And so now what we're going to say is sig digs, which is 3 sig digs, so 0.935 meters per second squared. So it rounds up. and that would be our final answer. All right. I hope this video helped you understand the basics of forces and some basic examples, and especially all the different types of forces and the steps to take to solve these questions. I hope this video helped, and good luck.